Greetings and welcome to lecture 21 on the course Introduction to Fourier Analysis. On the previous lecture we verified that the convolution between a tempered distribution lambda and a Schwartz function phi is an infinitely differentiable function which is polynomially bounded. Recall once more that this convolution was initially defined as a function on Rd whose value at the vector x in Rd is given by the distribution lambda evaluated at the Schwartz function tau x of tilde phi. Since the convolution between lambda and phi is a polynomially bounded function, which we may temporarily denote by f, we may associate to it a tempered distribution in the usual way. Lambda of f evaluated at the Schwartz function psi equals the integral of f times psi, which further equals the integral of the convolution between lambda and phi times psi. On this lecture, we are concerned with calculating the Fourier transform of this tempered distribution. We already know that this object is a tempered distribution, and Theorem 4.22 gives a more explicit expression for it. Let once more lambda be a tempered distribution, and let phi be a Schwartz function. Then the Fourier transform of the convolution between lambda and phi equals the Fourier transform of phi multiplied by the Fourier transform of lambda. The first remark here is that the right-hand side makes sense. It is the product of a Schwartz function and a tempered distribution, and hence a tempered distribution. Second, it is worth pointing out that while the convolution between lambda and phi is a smooth function, there is no guarantee that the Fourier transform of the convolution would again be induced by some function. As a familiar counterexample, let lambda be the tempered distribution induced by the constant function 1. Then, if phi is any Schwartz function, we may infer from Theorem 4.22 that the Fourier transform of the convolution between 1 and phi equals the product of the Fourier transforms of phi and 1. However, in proposition 4.15 we computed that the Fourier transform of the function 1 equals the Dirac measure. Consequently, the right-hand side here is a weighted copy of the Dirac measure, and it is generally not induced by any function. The only exception is where the Fourier transform of phi vanishes at the origin, in which case the right-hand side is the zero distribution. At the risk of emphasizing the obvious, Theorem 4.22 should be understood as an equality between two tempered distributions, namely the Fourier transform of the convolution and the product of the Fourier transforms. The proof of Theorem 4.22 requires one rather non-trivial lemma, Lemma 4.23. The plan is to state this lemma now and then use it to prove Theorem 4.22, but postpone the proof of the lemma to the next lecture. It will easily fill one recording. In Lemma 4.23, let mu be a finite Borel measure on Rd with compact support. This support is denoted by the letter k. Then let phi be a continuous map from the set k to the space of Schwartz functions equipped, as usual, with the metric d. In our practical application, phi of x will be something like x maps to tau x of psi for a fixed Schwartz function psi. The measure mu and the map phi are now used to define another Schwartz function by the formula integral of phi x d mu x. This notation can be rather confusing at first, so we'd better examine it carefully. Here, phi of x is a Schwartz function for every choice of x. So phi itself is not a Schwartz function. The integral means, informally speaking, an average over all the Schwartz functions phi of x, weighted by the measure mu. To be more precise, the value of this average Schwartz function at the point y in Rd is given by integrating the values of the functions phi of x evaluated at y with respect to the measure mu. Once you understand what the formula means, it is not difficult to check that such an average indeed defines a Schwartz function. Of course, this is based on the assumption that mu is a finite and compactly supported measure. We leave the details as an exercise. Now that we have explained the concepts, let's see what the lemma actually says. The only claim is that if lambda is a tempered distribution, then the value of lambda evaluated at the averaged Schwartz function is given by an integral over the values of lambda at phi of x d mu x. In other words, the linear continuous map lambda commutes with integrals of Schwartz functions, at least if the integration is done with respect to a fairly nice measure mu. With lemma 4.23 in hand, we may now prove theorem 4.22. Let lambda be a tempered distribution and let phi be a Schwartz function. As you may recall, the claim is that the Fourier transform of the convolution between lambda and phi agrees with the product hat phi times hat lambda, in the sense of tempered distributions. To verify this, we need to show in principle that if psi is any Schwartz function, then the Fourier transform of the convolution acting on psi equals the product of hat phi and hat lambda acting on psi. As it turns out, we will only prove this equation for Schwartz functions psi of a rather special kind, namely those which arise as Fourier transforms of test functions. In other words, we will assume that psi can be written as hat of eta, where eta is a test function. Recall that test functions were, by definition, smooth and compactly supported functions. Let's first justify why it is sufficient to show that the two distributions agree on Schwartz functions of this special kind. The first point is that the space of test functions is dense in the space of Schwartz functions, S, D. We haven't needed this fact earlier and have therefore not mentioned it before, but the proof is quite straightforward. For the details, see Theorem 7.10a in Walter Rudin's book Functional Analysis. The only idea in that proof is to multiply a general Schwartz function phi by a smooth cutoff function psi of r, supported on a ball of radius r, and then show that the products tend to phi in the metric d as r tends to infinity. Next, we observe that the Fourier transform map phi maps to hat phi defines a homeomorphism from S, D to S, D. We have explicitly mentioned in lemma 4.11 that this map is continuous on S, D, and it follows from the Fourier inversion theorem for Schwartz functions that the map is actually a homeomorphism. Now, in general, a homeomorphism sends dense subsets to dense subsets. Therefore, since the space of test functions is a dense subset of S, D, also the images of test functions under the Fourier transform form a dense subset of S, D. We denote these images by hat D. This is finally the statement that we need. If two tempered distributions agree on the dense subspace hat D, then they are the same tempered distribution, simply by continuity. We will apply this fact to the tempered distributions hat of lambda convolved with phi and hat phi times hat lambda. If we manage to show that these distributions agree for all functions psi in the space hat D, then they are the same distributions as we claimed. We then proceed to prove the equality of the distributions on the space hat D. Fix a Schwartz function psi, which can be written as hat of eta for some test function eta, and start from the left-hand side of the claimed equation. First, by definition, the Fourier transform of the convolution acting on psi equals the convolution acting on hat psi. But the convolution is just a function, so this expression means, by definition, the integral of the convolution multiplied by the function hat psi. At this point, we take advantage of the information that psi is the Fourier transform of eta. Namely, the Fourier transform of psi is the double Fourier transform of eta, which by the Fourier inversion theorem equals the tilde version of eta. It will be important to note that since eta was compactly supported, also the tilde version of eta is compactly supported. Finally, here we just plug in the definition of the convolution between lambda and psi evaluated at x. As you may recall, this equals the distribution lambda acting on the Schwartz function tau x of tilde phi. Next, we use the compact support of tilde eta. Denote by k the compact support of the function eta. With this notation, the integration above can be restricted to the set minus k, which is still a compact subset of Rd. Therefore, we have now deduced the following formula. The Fourier transform of the convolution between lambda and phi acting on the function psi equals the integral over minus k of the function lambda evaluated at tau x of tilde phi times eta of minus x dx. We are almost at the point where we can apply the previous lemma, lemma 4.23, but we do one final modification. Namely, if x is a fixed vector in minus k, or even in Rd, then eta of minus x is just some complex number, and it can be pulled inside the distribution lambda by linearity. Once we do this, we see that the Fourier transform of lambda convolved with phi, evaluated at psi, equals the integral over minus k of lambda acting on the function eta of minus x times tau x of tilde phi dx. Now the expression is exactly of the form where lemma 4.23 applies. Let mu be the compactly supported measure obtained by restricting Lebesgue measure to the set minus k. And let capital phi be the Schwartz function valued map on Rd, which sends a vector x in Rd to the Schwartz function eta of minus x times tau x of tilde phi. We leave it as an exercise to check that the map capital phi defined above is indeed a continuous map between Rd and the space S, D. With this notation, we may apply lemma 4.23 as follows. We start with the integral we saw above, namely the integral over minus k of lambda acting on the function eta of minus x times tau x of tilde phi dx. Then we recognize that lambda is precisely acting on the function capital phi of x, and the integration is with respect to the measure mu. Therefore, lemma 4.23 states that the tempered distribution lambda can be pulled outside the integral. The resulting expression is lambda evaluated at a certain Schwartz function, which is the integral of the functions eta of minus x times tau x of tilde phi, integrated over all x in minus k. We abbreviate this function by capital F in the sequel. We will next find a much simpler expression for the function capital F. Fix a vector y in Rd, and first use the definition of the function capital F. The value of f at y is the integral of the values of the functions eta of minus x times tau x of tilde phi evaluated at y, and then integrated over x in minus k. Next, recalling that eta was supported on k, we may now remove the restriction to minus k from the integral without affecting its value. This restriction to a compact set was only needed to make legitimate use of lemma 4.23 above. Next, we spell out the definition of the function tau x of tilde phi evaluated at y. This is nothing but phi at x minus y. The resulting expression already starts looking like a convolution, and we finalize the impression by making the change of variables from x to minus z. This way, we arrive at the integral of eta at z times phi at minus y minus z dz. This expression is simply the convolution of eta and psi evaluated at minus y. We choose to write it as tilde of the convolution evaluated at y. Now, comparing the left and right hand sides of the chain of equations, we find that the function capital F is nothing but the tilde version of the convolution between eta and phi. We are then nearly done with the proof. We continue from where we left off earlier. We had already showed that the Fourier transform of the convolution between lambda and phi, evaluated at the function psi, which by the way equals hat eta, is the same as lambda evaluated at the function capital F. Next, we plug in the formula we just obtained for the function capital F. We find the value of lambda evaluated at the tilde version of the convolution between eta and phi. We have seen in previous lectures that the convolution between Schwartz functions is still a Schwartz function, so the action of lambda on this convolution is well defined. Next, we apply the Fourier inversion theorem for Schwartz functions once more. The tilde version of any Schwartz function can be rewritten as the double Fourier transform of that function. And in particular, this holds for the convolution between eta and phi. One of these two hats above the convolution we move above lambda, just using the definition of the Fourier transform of lambda. After this, we are still left with one hat over the convolution, and the process that we use that the Fourier transform of a convolution is the product of Fourier transforms on the space of Schwartz functions. And this was proven in the previous lecture notes, proposition 3.8. Now we have arrived at an expression which equals, by definition, the value of the tempered distribution hat phi times hat lambda evaluated at the function hat eta. Finally, we compare the left and right hand sides of the preceding chain of equations. And this comparison shows that the tempered distributions we were interested in agree on the space hat D, consisting of the Fourier transforms of test functions. Since, as we discussed, this space is dense in S, D, the two tempered distributions also agree on all Schwartz functions. This completes the proof of Theorem 4.22. On the next lecture, we will focus on establishing the key technical step in the previous proof, namely Lemma 4.23. This completes lecture number 21 on the course Introduction to Fourier Analysis.